Okay. All right, today we're going to be looking at the code for the Romi robot. This is just the default template. We're going to look at some of the places where we can edit things and make changes to it. So we can start figuring out what tasks we actually want to be able to be doing with our robots. So the main structure of this program is just like it is on our competition robots. We have commands. They have a sensors folder that they've built. We normally call it drivers on our competition robot, but sensors works too. It's just kind of, this is any code that just interfaces with some bit of hardware that we would need to use over and over again. So if we have a different little light sensor or something that's able to detect balls on the robot, we might have a file for that. We have a file for like how we interact with the limelight back and forth, like our camera that we use. Any sort of hardware interaction type thing, we have some file. Like I said, it's called drivers on ours, but it's the same general concept. This is the code that they use to interface with the gyro on the Romi, so we shouldn't have to actually like edit this very often. This is pretty much part of their kind of what WPILib people write for us. So it goes through and figures out how to actually get the gyro rate and angle. So it basically tells us how far the Romi has turned since we've reset it or since it's turned on. So this is very useful if we're trying to figure out how to turn 90 degrees or so. This lets us do that pretty easily. We can do get angle Z. It's normally the Z axis that we care about. It's the one pointing up and down through the middle of the robot. X and Y would be the robot tipping back and forth or rolling side to side. If it was like twisting. Okay. And then we can reset it too. So if we get to some point or if we know we're starting up, we can reset everything back to 0 for the angles that we need to get. And that will let us do like a new 90 degrees or something without having to figure out where we already were. Okay, so the kind of basic stuff that, or the sort of default stuff that exists for all of the robots, including our competition robot and the Romi, that are all the same, is there is a main.java that for the most part we don't ever touch. All this does is start our robot base, which is what robot ends up taking. So our robot.java is basically calling something that's in this robot base thing. So you should never have to touch main, unless something very strange happens. But you'll probably talk to me about it before we ever get there. Robot.java, for the most part, we're not going to use very often. There are some things we may need to do in here. It just kind of depends on what we're doing with the robot. A lot of the stuff in here will just get to where we're calling other files that we write. So we won't do a ton of code in robot.java directly. Most of the time, we may add a few things. This is kind of where we can see the structure of the robot. Robot init is the very first commands that happen as soon as the robot turns on. So in this case, it makes a new robot container, which is kind of where all of our specific stuff to our robot happens. Robot periodic happens continually through the entire time the robot's running, no matter what mode it's in. So whether we're in, whether the robot's disabled, in Teleop, or autonomous, whatever's in robot periodic is just always running. So you have to be really careful with what is running here, since we basically will never stop it. Even if we're disabled or in Auton, it's always running. So we kind of just always have to be conscious of anything that gets put in here. Right now, the only thing that's actually in there is the command scheduler, which is how we can run our different commands on the actual robot, and it makes sure that it keeps running continually while the robot's running. It's always figuring out what command should be running no matter what. And then we have some more specific ones that don't get used very often. You can see these are empty on the Romi robot, so they're not used at all. Disabled init is basically the first thing that runs when the robot enters disabled mode. Disabled periodic is just whatever runs whenever the robot's in periodic. In our actual competition robot, we probably use these more often than we will on the Romi, because a lot of times we're setting stuff up, because basically disabled runs before the match actually starts. So once we power on the robot and we set it on the field, anything that we want to run and be able to interact with the robot with needs to be either in disabled periodic or robot periodic, or it won't be running until the match actually starts. So some of this is some interface code for like smart dashboard sometimes if we're putting out values. We may have some other things to clean up to make sure everything's ready for when Auton or Teleop starts. So a lot of these go in when we're actually doing kind of more complicated things with the actual robot. We probably won't do too much in here with the Romi, as it's small enough that we can kind of leave it enabled and do more of our stuff anyway. So a lot of what we'll end up doing is in robot container. And then you get the same thing for autonomous. You get an autonomous init. So this is the very first thing that runs when autonomous starts. In this case, it's allowing us to select the autonomous command. So robot container, we have this method called get autonomous command. And when we change what command is returned from this, it's the one that will actually get run. So it's mautonomous command.schedule, which means it's going to get run by our command scheduler right here, this command scheduler to get instance.run. So that's how we basically start our autonomous command, so we know that that exists. We don't really have to touch that until later at some point if we need to make a more complicated autonomous selector. So if you wanted to be able to easily select between like a variety of different autonomous modes without having to re-download code, you could change what happens in here to build that system in if you wanted to. You could also change it in this get autonomous command too, and that would also let you change how it selected its command and things as well. Autonomous periodic doesn't need to run since we're already running the command scheduler. If we don't have anything else that specifically needs to run autonomous, it can be empty. And then Teleop init is the first thing that runs at the beginning of Teleop. This little line of code in here or this little couple 3 lines of code, basically all it says is if there's an autonomous command running right now, we need to stop it because now we're in Teleop. If you don't have this and say you're in the middle of a match or even with your Romi was going and you wanted to switch it out of autonomous, you wanted to switch back into Teleop, it wouldn't actually do it until it would just keep running whatever the autonomous command was until it finished. So if you just told it to go straight forever, it wouldn't actually ever cancel unless you explicitly tell it to cancel. So it doesn't really know what mode it's in or anything. It doesn't really care. Once the command is scheduled, it'll stay scheduled forever until you explicitly tell it to stop somehow, or there's some condition inside the command, whether that's a timeout or a wait for like a sensor or something like that, then it'll actually stop. So again, we shouldn't have to mess with too much in here. This is kind of the same thing. Again, we have a teleop periodic. I don't know if we'll ever use test mode on the Romi or not, but it can be useful on the competition robot. The real meat of what we want to talk about today, most of it happens inside robot container, and that's where a lot of what we'll edit is either in robot container or we'll edit what happens inside of our actual subsystems and the commands for those subsystems. So robot container is how we kind of specify everything that goes into the specific robot. So we have our specific subsystem setup. So we have Drivetrain and onboard IO, which are the same subsystems we have here. These are the 2 files that they've written already for us for the Romi. We establish which sort of controller we're going to use. So in this case, they use a joystick. mController equals new joystick 0. So it's the first joystick on the driver station or on the simulator. That's how we know it has to be the joystick 0. So if we wanted to change that, or if we wanted to have like multiple controllers like we do on the actual competition robot, we could copy this and add another joystick. So if we wanted to have an operator controller, we could have a separate one. We could make it op controller or something like that. Op controller. And then we could make it joystick 1, and we'd have the second joystick that then we could reference and use separately. So if we had to like change the speed of something, or if our Romis got more complicated and they had added arms or intakes or anything else that we wanted a second driver to use, we could do that. We could do it just in a test setup if we needed to be able to see what happens if you hit different buttons or moved it in different ways. You could have a separate controller setup to do that. And it's easy enough to just write out new controllers and change the name of that variable to make it new, and then change which port you want to use it on. This specific call right here, the comment above it kind of tells you what it does. It creates a smart dashboard chooser for the autonomous routine. So this lets us choose which autonomous mode we want to run based on the smart dashboard. So if we have multiple different autonomous modes, we can assign them in a little list and choose them from the driver station computer instead of having to have any like buttons or switches on the actual robot to set it, or re-downloading code every time. This lets us do it from the beginning, or this is one bit of the code that'll let us do it. There's a little bit more later on, but it's just up here since this is where we define all of our variables and class instances and everything else. Okay. Robot container, since this method has the same name as our file, that means this is the constructor. So this is how we, this is what gets called when we make a new robot container. We did that over in robot. We made a new robot container right at the beginning of robot init. So the very first thing the robot does when we turn it on is it makes a new instance of this whole robot container class. And the first thing it does when it does that, it runs the constructor, and it does this method called configure button bindings. So the very first thing we do upon running is it's going to create an instance of this. So it means it's going to create all of these objects. We're going to get a drivetrain, an onboard I/O, joystick, and sendable chooser. Those are going to get made. And then robot container is going to call configure button bindings. So now this method is what's going to get run right after it does that. All right, so now that we're in configure button bindings, this is one of the places that we do modify quite a lot in the code. And this is one of the places that I look if I'm bringing up another team's code and I'm trying to figure out kind of what their robot's supposed to do or what they're trying to get it to do. This is one of the first places I start reading and understanding kind of what's going on and what their intent is for their program. Especially it's one of the places that you can modifying some things and changing things can dramatically affect how the robot behaves, and how, especially for what it's doing with the operator, because configure button bindings is pretty much how we tell what each joystick button does to each command on the robot. Or in this case, even drivetrain and things too. So because configure button bindings is called first, they also use it to call a default command for the drivetrain. So we have a drivetrain subsystem, and we basically tell it, no matter what's happening, your default command is this get arcade drive command. So, and this is it returns the command, which is how they're able to do that, which is fine. They actually write it inside of robot container, which is a little somewhat awkward. It's not a big deal the way they did it. I don't think we've done this specifically in a Spectrum robot before, but basically this lets you have a place where you can modify what the default command is for the drivetrain kind of inside robot container, so you don't have to have your own they didn't make their own command for drivetrain or for their arcade drive. They could have. That would be another way to do it. You could make a whole command file, which we're going to look at in a little bit, and you could just reference that if you wanted to. But instead, they basically do make the command. They just do it in line here. So yeah, arcade drive is a command, but they just they pass all of the arguments and things inside of it, which is a little bit weird. We have to talk about like how some of the inline operators and things work. Yeah, because they basically need to have this supplier thing. So we'll go into that in a little bit later. But basically, it allows them to pass methods directly and not just the actual value. We'll get to that. I'll come back to that in a second. What I want to go through first before we get too far down that rabbit hole is the normal process, or like the rest of the process of how configure button bindings work. Ideally, most of the time we're going to do things like this, where we're basically, depending on what happens to a button, something's going to occur, or something's not going to occur or get turned off. Like we can turn something on or off. So if we have an intake, we can hit a button and it'll turn on, and when we release, it's normally that command is canceled, so then the intake stops. Same with like the ball launcher or the climber, anything that we have just controlled on buttons and they're running on commands that we write, normally get run based on buttons. They have an example of how to use some of the buttons. This is actually the onboard IO, so this isn't using it from a joystick. This is using it directly from a button on the Romi robot itself. So they have to make a new thing called a button. So there's a button class in WPILib. The M onboard IO, which is referring to our actual subsystem class, and then in there's a get button A pressed. Now that we've made this onboard button A, right? These are like two separate things. I don't think this is like a continued line or anything. They did a little odd. They did this thing where you can decorate it, which is a little strange. It's definitely somewhat valid. What this is doing is the exact same as, let me see, it would be the same as this, just so we're clear. Oh, too many. So that code and the code they already had are identical. They just didn't have to type the onboard button A again. I normally like this better. It's cleaner than the other one where you think that they're in some way related. To my knowledge, they are not. I don't think I have that wrong. Right, they're related because they're acting on the same button object, but otherwise they're not. Like this one doesn't necessarily affect this other one. They can be two separate things. They could be called at two completely different points if you wanted to. This is ideally the point where we would. And this is how I would normally write it, not the way they did. But if you're reading other people's code, or if you prefer that syntax, I'm not going to get. If it works, it's fine. Like we can all understand it. This is just a little bit more explicit, in my opinion. But it's up for debate. There are other people who do it the other way. But yeah, so all this basically says is when the button is pressed, or in this case, when active, it's going to print, so you actually see it on the little, why am I blanking on what it's called? There's a little output, the console output from the RoboRio. The RoboRio log file will show it too. And in this case, it'll just say whatever string you pass it. So in this case, button A pressed or button A released. And those come out fine. They do have to be an actual command. Print command is one of like the default commands that WPILib exists for us. So anytime we want to kind of test control logic, it's very easy just to make these new print commands and have them replace what would be like bigger, complicated commands on the actual robot. But if we just need it to be like, hey, new print command, arm going up or something, and then if you're testing out the logic, you would be able to see it say arm going up without having the robot actually move at all. So especially for during testing and prototyping and making sure that you actually have your code right and interface right, these are super useful to just be able to do new print command, whatever you want it to do. Anytime you're trying to like debug or work through any sort of problem or logic on the robot that you're trying to get to work, very handy to just be able to do new print command. And then they also in here, which again, I'm not really sure why they chose to put everything in this. Like, it's called configure button bindings. It clearly should just configure button bindings, but they somehow decided that setting up some of the smart dashboard options is also a reasonable place to do it. In our default competition robot code, we have a separate place where we set up all of our smart dashboard things. So the same thing that this is doing, we have a specific place for it. We have a dashboard class in ours, just because it ends up being much longer. If we ended up trying to copy their model, instead of 3 lines, we'd have 40 something, depending on the robot. A lot of times there's a lot of different stuff that we're setting up and timing and things. But it does work here, and this is another one of those times where, like, sometimes the way you do it doesn't necessarily have to be completely correct as long as the outcome is right. For something as small as the Romi, it probably makes more sense to do something here where it's easy to find and edit than it is to build out a whole nother class file and do all of the kind of overhead for something that's not going to be used all that often. So what this actually does set up for us, though, is it sets the default option for the M chooser, which was how we're going to select the different autonomous modes. So it defaults to the auto routine distance, and it creates the instance of the command to do so. So the new autonomous distance command with M drivetrain, and then it adds an option for a auto routine time. It makes that new command and with the same drivetrain option. And then it puts the chooser on the dashboard. So smart dashboard.put data M chooser will send it there. So then we're able to select the different values. And we'll eventually, we use that in this next part here where we can actually see the command that lets us get the autonomous command, which is just mchooser.get selected. So this will return which of the things is currently selected whenever this command runs, this get autonomous command runs, which is in the robot again. Down here, we saw it in autonomous init. So it runs this get autonomous command, and it returns either the autonomous distance or the autonomous time based on whichever ones we select. So if we start adding autonomous routines, which is something you guys could definitely do with your Romis, we could start adding an autonomous maze or an autonomous whatever we wanted, or eventually we can get to adding the autonomous modes for the different navigation challenges for FRC. So if we're doing the slalom or the barrel run or whatever, we could just add in mchooser.add option, and you can just follow the pattern the same way where we can do bump path or whatever they're called. And then you would create a new object for whatever the command that you would go and write afterwards. You do new, whatever the command name was if you had created one. Okay. All right, we're going to look at how the subsystems are set up and then how the commands interact with them. And then we can work on, that should give us foundation for actually writing our own commands for the drivetrain and for the Romi, and we can start making it do a lot more and working on the actual robot logic and things. So inside drivetrain, we have our all of the imports. So these are all the things that get worked through. These are all like the other classes and part of WPILib that we actually reference inside this drivetrain subsystem. There's a lot of specifics that are all done specifically for the Romi, so we don't have to edit most of this because this drivetrain exists and all the Romis are the same. But when we go to make this for any of our other competition robots, we will have to figure out how those robots are set up. So we'd have to know where the motors are plugged in, where the different sensors for the drivetrain are plugged in, all of those types of things. With the Romi, we don't have to since they all are the same. So it creates a couple, these are basically just constants, right? Because they're private static final. So these are static and final. So final means they can't be edited. So this will always be the same number, but these help it so we don't have to type that number whenever we need it down here later. Then we set up the actual hardware, so we have the motor on each side. So we have a left and right motor. They run them as they use the Spark speed controller library, which isn't directly true. Like there's not an actual Spark, which is one of the types of actual motor controllers we can run. But because the Spark is relatively simple and just takes a PWM command for forward and backwards, it takes basically the same commands as the motor controllers that are built into the Romi. So they're using the Spark as the placeholder since they didn't have any of they didn't write a whole separate motor controller class just for the Romi when the Spark will do what we want basically. Then we tell it where the encoders are plugged in. So we have these two, we have a left and right encoder that are specifically wired into specific digital inputs on the Romi board. So the left encoder is 4 and 5, the right encoder is 6 and 7. So now we don't have to know that anywhere else. We can just refer to M left encoder and M right encoder all the way through the drivetrain class or the drivetrain subsystem, and it'll know where they are and how to get that information so we can know how far the wheels have turned or how fast the wheels are going. They create a differential drive object. So this is another useful part of WPILib that kind of already gets created for us. So when we pass the left and right motor, we can already know how to drive and steer. There's a bunch of methods that are really useful, including like arcade drive. So all of this is kind of already set up for us, since it's something that happens so often with robots that you have a left and a right drive and you need to move around. A lot of that code's already done for us. There's also one for swerve drive. There's one for mechanism drive. They all kind of already exist, and at least the basics of getting your robot moving are kind of already written for you for WPILib. The drivetrain also includes a gyro, which again tells us how far we've turned or how fast we're turning. It includes an accelerometer, which isn't used for a ton of stuff, but maybe if you wanted to tell if the robot possibly bumped into something, you might be able to tell. If it fell, you might be able to do a few different things with the accelerometer. If it was like, if you wanted to see if the robot got like shook, anything that like that shake, quick acceleration back and forth, that type of thing you could possibly tell with the accelerometer. It normally doesn't get used a lot in our bigger robots, but maybe we could find interesting uses for it on the smaller one. All right, so now once we kind of have all of that set up and we've built out, or we've like kind of built all of our objects, we have the constructor for the drivetrain. The first thing it does is it kind of sets up how the encoders are to work. So we give them some variables to help us. So they have the wheel diameter in inches and counts per revolution. So we can figure out actually how far the robot moves every time the encoder pulses. So we send that to both the left and right encoder, and then we reset the encoders to 0 right as the robot starts up, because we know it hasn't moved at all. So then we can figure out how far both the left and right wheel has moved since we actually started the robot. Arcade drive is one of those methods that's built into the differential drive object, and it lets us take a single value for forward and backwards for both wheels, and then it takes a left and right rotation value and lets the robot turn left and right. Anytime you want to like see how these things work, you can right click and do go to definition, and it'll show you a little bit more. You can actually go through and look at all the math if you want, and you want to dig deeper to figure out how a lot of this works. You can do that pretty easily. For a lot of it, some of the time until it breaks or until you want to change it or make improvements, a lot of times you can just use it. If it's working, great. But then as you get more curious, or as you find if there's something that's not quite right, or you're trying to figure out how to make something or change something, then you start diving deeper and reading more and figuring out how it all works. We already talked about reset encoders. These are what are called like the getter methods. So this is how we get information out of our subsystem. So we have a get left encoder count, a get right encoder count, a get left distance inch, so we know what unit we're in, get right distance inch, and all of these are pretty easy. They just are literally just like mapping other methods throughout the objects that we have. So they just map onto the different encoders, and they're almost just like renaming those methods for this object. But it makes it easy so we know where everything is because we know it's all in our drivetrain object. We kind of collected it all in one place. We have another one, get average distance inch, so you can just get an average distance for how far the robot has traveled between both wheels. There's some more getter methods for acceleration, some more for gyro, and then we have a reset gyro here too. So instead of always having to like know which gyro we're talking about or anything, because we all have it set up in our drivetrain object, we can get everything about the motors and we can send them different values. We can get all the information from the encoders, we can get all the information from the gyro, all packaged together in this one drivetrain subsystem. If we were expanding this, we would do the same thing on our competition robots for like the intake. They would have the pneumatics that move the intake. They would have the motor that moves the intake. If we had any sensors, all of that gets built into the subsystem class. Same with like the elevator or the launcher. We kind of everything, all of the electronics that package into any of the different subsystems on the robot, we include all of their information in that same class, so we can always know how to access it really easily, and how to modify it in the ways that we want. Once we have that subsystem set up, we then can create commands that interact with it. So some of them are simpler than others. So we have the arcade drive command. So it's going to act on the drivetrain subsystem. It's going to ask for some way to be able to know how fast. It needs an axis to be able to tell it basically like its throttle or speed, forward or backwards. And then it needs the same thing for which way to rotate. It does commands can require a subsystem. So in this case, arcade drive does require drivetrain. What that means is no other command can be operating on drivetrain at the same time, which is a good thing. We wouldn't want arcade drive to be running and one of our autonomous routines to be running at the exact same time. We don't want like two different commands telling the drivetrain to go two different places. The motors get unhappy. You have things like twitching back and forth. Like it's not good. That is one of the errors that you will see sometimes, especially if you have like really twitchy motors or something where it just like looks like it's telling it to both go forward and stop at the same time. It's possible you have two commands trying to drive that same motor at the same time. Commands are all set up kind of in the same way. You have an initialize, which is the first thing you do with the command. You have an execute, where it's going to run this over and over again every time as long as the command is running. Then you have an end, which is the last thing that happens when the command finishes. It's like how you kind of clean things up. So it may be like turning motors off, which is very important. Which I'm surprised they actually didn't do here. It's not like super critical in this specific state, but it is one of the things that we would always do is we would come in and if like this is one of our commands for the motors, we would make sure that if for some reason this is ending, we want to stop the motors and then the next command will tell them where to go. So we would normally we could do like M drivetrain. Arcade drive works because you can just tell it 0 and 0, and then it wouldn't. We would know that the motors are fully stopped when this command is over. Because in theory, the last thing we could have sent them could have been like full speed forward. Something else is taking over. We don't know what that something else is, so most of the time we want to tell it to turn off just in case we're going somewhere else. In practical terms, this won't happen because earlier we set up that this is going to be the default command. So even if it stops, if nothing else is taking over properly, it's going to come back to here eventually or very quickly. So normally it's not an issue. But in most of our methods, we always want to make sure we stop our motors, or most of our commands, we want to make sure we're stopping whatever motors we possibly start in end. And then is finished checks if the command should end. So depending on what the command is, maybe it's a command telling it to drive a certain distance, or you're intaking a ball until, or you're trying to like run the intake until a ball hits some sensor or something. You could have some bit of logic here that returns true whenever you're ready for the command to actually stop. And then that would stop the command and it would send it somewhere else. Because this is the default command for the system, it probably doesn't need an is finished. You want it to run basically forever, which is totally fine. There may be some weird cases where that doesn't happen, but for the most part, we're good here. Some of these other ones are a little bit more complicated. Let's actually skip command group real fast. We'll come down to, we can come down to like drive distance. So drive distance is a command that acts on the drivetrain too. So it needs to require the drivetrain, because if it doesn't require the drivetrain, arcade drive could still be running, and you could have them both run at the same time, which you don't want. So as long as everything that needs to like have full control of the drivetrain and can't run with something else, you add it as a requirement, and the program won't let it. So as soon as drive distance gets called, it'll cancel arcade drive and let drive distance basically take over. In here we have as our arguments to create the command drive distance, we have a speed and an inches. So we're going to tell it how fast we want it to drive and for how far. Again, they're kind of all set up in the same way. So we have an initialize, an execute, an end, and an is finished. Our initialize, they actually do this here. So they do m drive at arcade drive 00 at the beginning. So instead of having it happen at the end of arcade drive, because this wasn't here before, they're just making sure it happens at the initialize of the other one. Both methods work. It's probably good. It's reasonably good to do this anyway, just to make sure we've told the motors to stop. They're going to reset the encoders, so they're going to put them back to 0 so that we know we can have a place that we know we're starting from. In execute, we're going to drive forward at whatever the speed is. And then when we finish in this one, we do arcade drive 00, so we know that we're stopped. And the way that we actually get to that end is we check this is finished call. So we're going to return math.abs. So this is absolute value. mdrive.get average distance greater than or equal to m distance. So it's checking, is the average distance in inches greater than or equal to however far we told it to go. So what is useful here is you would want your by setting dependent, if you want the robot to go backwards a certain distance, you would just change it in speed and not in inches necessarily. Because once you changed it in inches, if this was a negative number, you would always be greater than as soon as you're at 0. So we would want this to always be positive, but then this could be negative. We could be going backwards because our speed is backwards, and we're just going to flip it to basically that positive number with the math.absolute value, which if you have like -2, absolute value of -2 is 2. So then that would work. Yeah, so then as soon as we actually get past whatever distance we're going, say we're going 2 inches or however far we go, this would come back as true once it was actually greater than whatever our distance was, and we would stop this command. If that was just the last command, it would default back to arcade drive. If we had something following it, we would start that next command. So like in autonomous, no, that's arcade drive. In autonomous distance, this is a command group that assigns multiple commands together. So in this case, we have a drive distance. Once it finishes that 10 inches, it does a turn for a certain number of degrees. So it's going to turn 180 degrees, and it'll start doing that. then it drives another distance, and then it turns for another 180 degrees. So you can see that you could modify these to turn different amounts, to drive different amounts, to change speeds. You could do a lot by having these just in different orders for the command group. So this is what's called a sequential command group. So it waits for each one of these to finish and goes on to the next one over and over again. So for those of you with Romis, you should be able to basically take this information that we talked about today and make different paths based on modifying these commands. You could also make them run on different buttons if you want. So if you wanted to come in, you could make a different autonomous command. You could like make a copy of this. We could make this copy. We could name it something different. We could call it like, you could make an autonomous like dance if you wanted, whatever you want to do. You would change the name of the file. You'd change the name of in here. Will it automatically, rename file. All right. And then you could go through and you could change all of these to make it do whatever you wanted. So you could have it turn for a different amount. You could have it do more commands. You could have it drive further in different directions. There's a lot of different options for what you could do. In adjusting this basically and making the Romi do different things autonomously. Once you had a different thing, if you wanted to, you could add it to our autonomous selector. So this would be back where we come in here and we do this m.choose, or the m.chooser, sorry. And you could do add option, auton dance, there's an extra capital, all right. New autonomous dance m drivetrain. And now that would actually be on our chooser that we'd be able to run. All right, let's see if this will actually show up and we can see where the chooser and everything is. All right, so network tables. We can pull out our little sendable chooser and we have autonomous routine distance, time, and dance. So we could select which one it is. And now if we flipped over to Auton, it would start running that dance subsystem instead of the autonomous distance one.